Greetings and welcome to our discussion on computer networks. In this lesson, we're going to continue and build off the previous lesson by talking about a lot of the details that are happening behind the scenes. So we're going to talk about IP routing and how a message gets from the source to the destination. We're going to talk about routers and switches and the difference between these pieces of hardware. And then we're going to talk about a bunch of network protocols such as DNS, DHCP, and NAT. These are protocols that act behind the scenes, but they make networks a lot easier for us to manage and use. Finally, we're going to talk about networks that are wireless. And we're going to talk about the pros and cons about them, and then talk about the security implications that occur once you allow connections to occur over open airwaves. If you remember from the previous lesson, we talked a lot about how we get messages from a client to the server. And you remember that I used the analogy of an instant messenger conversation. So if a client wanted to request information, they would formulate a message that looks something like this. This corresponds to in this case, the HTTP protocol. And then we included a bunch of additional information that we need to get the information from the client to the server. So like the IP address and port, as well as our own IP address and port. Then we talked about how the server consumes this information and generates a response packet that corresponds again to the protocol and contains the information that we want. So we talked from the end to the end, but what we forgot to really talk about in detail is this part in the middle. And it really wasn't an omission. We're just going to go into more detail in this particular video. So in order to understand what's happening in this cloud, we need to get a better sense of what the internet actually is. So simply put, the internet is just a collection of networks. So if you think about the USAFA network contains literally thousands of computers, all of your computers, all of our computers out there communicating with each other internally. In addition, there are other networks that exist in the Air Force, right? So every base would have a network. And then we would take all of these networks and combine them into what we call the Air Force network. And if the Air Force has one, of course the other services have to copy, so every other service is going to have their own network. And collectively, we can think of all these networks as the DoD Information Network. Sometimes we call that the DoDIN. And if you think about the DoD is not the only people who have networks. For example, your internet service provider has a network for your home, so Comcast, AT&T, Verizon, all of them have their own networks. And inside, there are your networks, your home network, your neighbor's network, etc. And all of these other networks just represent hundreds, thousands, millions of networks that are out there. Collectively, all of this is the internet. So we've talked a lot about, how things are communicating from the source to the destination, but it makes a lot more sense when you see that in order for a message to get anywhere, we have to go across a lot of different networks in order to get to the destination. So there's a lot of details going on, and that's why we're going to focus on it for this lesson. So let's imagine that we want to actually get a message from one computer to another. So let's say from this computer inside the USAFA network to a computer in our house. In order to do this, there's a lot of details. We're going to talk about each one of these in turn, but the first thing we're going to talk about is the physical connections. How are all of these networks connected to each other so that they can share information? For this class, we're going to focus on two types of what we call backbone devices: switches and routers. There's a lot more, and if you become a computer science major or take a networks class, you'll learn about them. But for this class, this is enough for us to get started. And I want to warn you before I start these discussions that when we talk about these devices, we're going to talk about the textbook definition. The router that you can buy at Best Buy does a lot more than what a router does according to the reading. So when you are talking about exams or questions, make sure that you use our definition and not what you think a router does, like the one that you have in your house, because that one is basically a router and a switch all combined in one. Now we're going to talk about each device. So a switch is basically a device that connects devices on the same network. So this is what an industrial switch looks like. You can have hundreds or maybe even thousands of them. There are tons of them in USAFA. Basically every squadron, I think, has a switch. And switches you can logically represent like this, that you have this switch in the middle and it's connected to all the devices, and you can have switches connect to other switches. So this forms the interconnections between all the computers within a network. All right? The next device we're going to talk about is a router. And a router is responsible for connecting networks together. So each router basically connects one network to another network. And then the routers learn how to forward messages between networks. So they basically learn how to get from one network to another. So here, for example, if we had 3 networks for the USAFA network and 2 Air Force bases, you would have the routers sit here and they would be connected to each other. There's no guarantee that every router is connected to every other router. Instead, this router, the USAFA router, would learn that it's connected to Peterson and Travis would learn that it's only connected to USAFA. So basically, they are figuring out if I'm in Travis and I need to get a message to Peterson, I have to send the message to the USAFA router, who in turn will know to send it to Peterson. So when you put it all together, routers and switches work together to get a message from the source to the destination. So in this case, we want to get a message from the blue computer to the yellow computer, and then the switches connect all the computers inside of a network. So what happens is this message starts from here, goes to the router. The router determines that the message isn't intended for a computer inside of this network. So what it has to do is it looks along its path and said, what's the best path to get it to its destination? And it may end up sending it to other routers. So this basically is all the routers on the internet, right? And you can actually see all these hops, and then they get to their destination, all right? What's cool about routers is that they can learn on the fly. So if something is broken along the way, so for example, this node is disconnected or it's just too congested, the router will actually still learn that the best route is now to use this one, right? And it can still get the message there. And that goes back to that packet switched idea we talked about last time versus circuit switching, right? So now that we've talked a lot about how the routers and switches work together, you can see that this diagram isn't accurate, right? We really don't have a direct connection. What we have is a ton of hardware that's in all of the networks. So if I want to send a message from this computer to this computer, the message basically has to go to the router inside of my network, which decides to go to another router, which decides to go to another router, which decides to go to another router. Each time we go to a router, we're jumping to another network, until eventually we get to our destination that connects to the actual specific computer. So now that we've talked about how messages actually get routed from one network to another, let's talk about some other details. So one that we glossed over last time was IP addresses. Remember that an IP address represents your location on the network, but we have two types of IP addresses. Private IP addresses, which are IP addresses that you can only see on your own network. So on our home network, for example, most IP addresses start with 192.168, and it's just a standard that IP addresses that start with this are intended for private use. And then there are public IP addresses, and these are visible to all the computers on the internet. There's actually an organization called the Internet Assigned Numbers Authority, and they're responsible for giving public IP addresses to make sure that nobody is using the same IP address. So in a private IP address space, every home can use this because you can't see those addresses on the internet, but the public ones, only one computer can have this IP address out there. All right, and if you go to Wikipedia, you can see this is a list of allocated IP addresses for the Department of Defense. This is just a subset of them, but you can see that basically if an IP address starts with 6, 7, 11, 21, 22, 26, 28, 29, 30, and 33, these are reserved for some form of Department of Defense use. So that's kind of interesting. So how does a computer actually get an IP address? There's basically two ways. One way is you could just do it statically. So I could give you an IP address, you go in your computer and you type it in. And you can actually go into Windows and say my IP address is 192.168.1.11. And that's fine. But the more common way, since you usually don't use that, is dynamic. So what happens is we assign a computer an IP address when it logs in, and then we basically let it use it for as long as it's connected. So the idea here is that as you move between networks, we can just keep giving you new IP addresses. So when you go to Starbucks, you get an IP address. When you go to Best Buy, you get an IP address, so on and so forth. The protocol that makes all this happen is called Dynamic Host Configuration Protocol, or DHCP. So the idea is that if your computer connects to a network, usually this is done in the router, so the router has like a little DHCP server. The computer will announce, I just connected, I need an IP address. The router will look and say, well, these are being used, but this one isn't. It'll send back the available IP address, the computer will configure itself, and then the router will say, this one's now being used. All of this happens behind the scenes. And what's cool is that DHCP actually leases you the IP address, let's say for like 24 hours. So this prevents IP addresses from being used, and then all of a sudden when you disappear, that IP address can be freed up again so that we can give it to another computer. When it comes to IP addresses, there are basically two versions that are in common use. The first one is IPv4, and this is the one you're probably the most familiar with. So it's 4 numbers separated by periods. Each of these numbers is technically an 8-bit number, so it's a value between 0 and 255. And there are 2 to the 32 possible addresses. When we originally built the internet, we thought 2 to the 32, which is a little over 4 billion. We thought there wouldn't be more than 4 billion computers on the internet. We were wrong. As of 2015, we only had 10% of these addresses left, and we've basically exhausted our supply since then. Our solution was to develop a bigger address. So this is IP version 6. This is what one of those addresses looks like. It doesn't quite flow off the tongue. Each one of these represents a 16-bit number, and there are 128 bits in an IP version 6 address. So 2 to the 128, in case you didn't know, is a ton of addresses. It's enough to give everyone 32 billion addresses and have plenty to spare. So IP version 6 was ratified in the 90s, but we're still using IP version 4 in a lot of networks, and the reason usually has to do with backwards compatibility. There's a lot of old computers and old networking equipment out there that only works with IPv4. So rather than try to flip a switch and make all those routers not work or all that equipment not work, we've decided to just try to support both and keep pushing towards updating the equipment until eventually everything is using IP version 6. But this leaves us with a problem, right? Now we have a dwindling supply of IP version 4 addresses, so how do we make them last? And one way to do that is using a technology called Network Address Translation, or NAT. And the general idea here is that we're going to take one address and share it with a bunch of computers. And you do this all the time in your home network. So for example here, in your home network, you'll all have these private IP addresses, and your router to the outside world will have this public IP address. So to the entire world, you look like this address. And you can actually see that. If you go to Google, for example, you type, "What's my IP address?" I just happen to have it here. This is what my IP address looks like to the world. But if I was to go and type ipconfig, you would see this is my private IP address. So you can see most home networks use NAT already. This does put a little bit of strain on the router. So the router basically has to be smart enough to know who's asking for information on the inside. It has to remember, for example, if this computer wants to go to Google, the router has to remember this computer asked for it, so it'll ask Google, get the web page, and send it back. So it has to remember who's asking for what, so it can direct that traffic the correct way. Now that we've gone over how the networks are physically set up and how we deal with IP addresses, now there's a little detail that we probably missed. How do we look up someone's IP address? So for example, again, if I go to Chrome and I want to go to a web page, I don't type 172.217.1.206, right? I actually just want to type Google and get there. So one of the challenges that we have is, how do we go from a word like google.com to an IP address? The way that we do it is using a protocol called DNS, and DNS basically converts names to IP addresses. So there are DNS servers throughout the world. When I talk about domains, I'm talking about like .com, .edu, .net, all of these. And in fact, here's a map that shows where they are. And these servers basically have a giant table of google.com is this IP address, usafa.edu is this IP address, right? So it's a massive table. So if you wanted to convert, for example, wikipedia.org into an IP address, the way that you would do it is your computer sends a request to the USAFA DNS server, and if the USAFA DNS server has that information, it'll send it back, but oftentimes it doesn't. So then it will go and ask what we call the root DNS. And the root DNS knows where, for example, like the .org DNS server, and it will return that IP address, and then USAFA can ask the .org DNS, where's wikipedia.org? It'll get back the IP address of the wikipedia.org DNS. That will get the IP address that we can eventually send back to the Ket laptop. So the idea here is that these DNSs, they are organized in a hierarchy, and each one knows something. So root knows where .org DNS is. .org happens to know where wikipedia.org's DNS server is, and wikipedia.org should know where this particular web page is, right? So that's how we organize it, so that there's not one computer out there who has to know everything about the internet. The last thing I'm going to talk to you about today is wireless. So wireless technology doesn't change things from a routing perspective. We still have switches, we still have routers, all that sort of stuff. It's just the medium through which that information transmits. But while there's no difference between a wireless and wired network from an IP routing standpoint, there are some pros and cons of using wireless networks. So one of the advantages of wireless networks is that they're extremely convenient. You just plug in an access point and everybody can connect. No need to dig trenches, lay cables, bust into walls, that sort of thing. The downside, though, is that you basically are now transmitting your information over a radio, which means anybody with an antenna can pick up that information and potentially know what you're talking about. Wireless networks tend to be slower. They're easier to interfere. If a lot of computers are transmitting over a frequency range, it's easy to overload that frequency range and now nobody can talk over it. And then in terms of security, it's hard to ensure that only good people or the people you want are connecting wirelessly. So when they originally installed Wi-Fi in Fairchild, what they discovered was that visitors on the chapel could actually bring their laptop and connect to Fairchild Wi-Fi. And that wasn't intended. They didn't think the range was that long. It just turned out to be. So there are a couple ways to secure, or at least take steps towards securing wireless technologies. One way is to just try to block the signal itself. So it's hard to constrain a Wi-Fi signal, but you can if you have enough money, time, and diligence. So here, this is what's called a Faraday cage. It's basically just a wire mesh that prevents all signals from coming in and going out. So this person in here, their phones aren't going to work, their Wi-Fi is not going to work. All right. This is what we do on every secure facility or classified information facility. This prevents signals from coming in and from people inside from being able to like take a picture of a classified document and email it. The signal just doesn't leave the building. There are other technologies that are probably a little bit more practical that you use in everyday life. So for example, most of you probably have a password on your wireless access point using WEP, WPA, or WPA2, which is the most secure. Basically what you're doing is you've created a way to encrypt your data. So that password is the key that's being used to encrypt your data. So people who are outside of your network, who are not connected to your access point, they can see the signals, but they can't read the data, right? The downside is that everybody who's connected to the access point can see it. So you just got to make sure that only the people who you want to connect to your access point know the password, and that's sometimes hard to do. HTTPS is a way for you to form a one-on-one connection to get information. So in this case, it's just websites. If I want to get a website from Google, I send an HTTPS query, and basically we share a key between me and Google, and then we are able to communicate securely with just each other. The downside of this is that that key travels over the network, so if somebody is able to grab it when it's en route, they can now start watching the conversation and collect that information. So the Air Force's solution is to use what we call virtual private networks, or VPNs. This is basically the same idea. If I want to communicate securely, I form a secure channel with my computer and the Air Force network. The only difference is we never share a key over the network. The key is in my CAC, and the Air Force has the other side of the key so that we can communicate without having to share. So somebody can be in the middle and they can see the signals, but they won't be able to decrypt it. Now that we've talked about some technologies that help us secure networks, let's talk about the threats that are out there. Reconnaissance is a huge deal, and it's pretty easy to do. So here, for example, you take a Pringles can, you shove a Wi-Fi antenna on the bottom, and all of a sudden your Wi-Fi antenna has 600-foot range, and you can connect to a hotspot from that far away. So the ways that you can stop people from doing this, you can't stop them from getting a Pringles can, but if you put a password on the network, it's hard for them to connect to it. And if you use HTTPS or VPNs, even if they can log into your access point, they won't be able to read the data. With sniffing, the same general idea. Someone logs into your network. So for example, at a Starbucks where there isn't really a password on the Wi-Fi, someone can just sit there with a program like Wireshark, turn on the sniffer, and just start listening for all the packets that are being sent, and they can get all the data. So again, the way to get around that is to have an encrypted channel. Use a VPN or HTTPS. Probably the best thing you can do is actually only connect to Wi-Fi hotspots that you trust. Probably shouldn't, do banking at Starbucks, right? Because again, anybody can log into that and start sniffing your traffic. Piggybacking is when your neighbor doesn't want to pay for Wi-Fi. But in all seriousness, it's when other people are using your Wi-Fi hotspot without your permission. The way to get around that is just to put a password on your Wi-Fi hotspot. Use WPA2 or another technology, even though WPA2 is technically the most secure. And the last one here is called man in the middle. And here what happens is a attacker injects themselves in between a conversation between a user and the computer they want to talk to. So the idea here is that the man in the middle can either, pretend to be this other computer, or could just relay the packets back and forth and just collect them all. So you may not even know that an attack is happening. The mitigations for this are pretty straightforward. Again, that secure communications channel will help prevent the man in the middle from being able to get any information, even if he can inject himself in there. And again, just connecting to trusted hotspots goes a long way. So I know it's a long video, but thank you. We made it to the end of it. We now know a lot more about networks and wireless networking than you probably ever thought you wanted to. So we talked about how packets are routed using switches and routers. We talked about DNS, which is the service that converts a name like google.com to an IP address. We talked about DHCP, which is the service that gives someone an IP address when they first join a network. We talked about NAT, which is a way for us to share one public IP address with a bunch of private IP addresses on a network. And then we talked about wireless security technologies and the potential threats out there. So if you've seen anything from the latter half of this video, is that even though we design networks to provide this exchange of information, malicious people can use them in unintended and harmful ways, which is why from now on we are going to be transitioning over to the cyberblock, where we're going to be talking about these issues in greater detail. So thank you for watching, take care, and I'll see you in class. Bye.